In the last video, we concluded with an example that was using an inconsistent system, but we also talked about being able to multiply both sides of an equation by a single value and using that instead. The idea is that if it is a line, you can have any multiple of that line and it would still be that line. So I wonder if there's a different way of solving some of these systems other than using substitution. So here's an example we actually saw already. We're going to do a different approach. So this one says, it gives us very specific instructions. Why we have to add, that's not completely clear, but we'll get there. Alright, so what we're going to do is follow the instructions. So multiply the first equation by 2. So that means we can look at the system of 6x minus 4y is equal to minus 1, and then 2x plus 4y is equal to positive 1. Okay, I did that, and then it says add the resulting equations. Okay, well, if I add them, what happens? This is 8x is equal to, and actually I made a typo, there should be a 2 there, minus 2. 8x is equal to minus 1, x is equal to minus 1/8. That was the same value I found as an answer for this system before, and then this led us to find the value of y. We can find it here again quickly. Plus 4y is equal to 1, and then so this is minus a fourth, and if I add that, I would get 4y is equal to 5/4, and consequently y is equal to 5/16. And so I would say the solution set is negative 1/8, 5/16, and that matches what we got before. Okay, so no big surprise here, but the method is a little different. Okay, so this method that we did is called the addition method according to the book. Some books call it elimination method, others call it addition by elimination. Nevertheless, just be aware of this method. Okay, so then what were the steps that we took to solve this system? Okay, see if you can detail those here briefly. So I have 5 steps, and there's kind of like 2 preliminary steps that you can take if you want to. If you want to, you can get things in standard form. Okay, that's just useful so that you can kind of line everything up and cancel it out later. And then clear fractions. Okay, we saw that at the last video. If you want, you can do that. But really, you want to multiply one or both equations by a non-zero constant so that one variable has opposite coefficients. That happened here with our y. Okay, we had opposite coefficients. And then we wanted to add the equations, right? Solve for the remaining variable, and then resolve for the canceled out variable, and then state our solution set. Now I could check this, but I checked it before, so I'm not going to check it now. Okay, now more importantly, why can we arbitrarily add these equations? Okay, that's the big sticking point. Geometrically, what happens is if you add equations, you eliminate, effectively if you add the equations and you eliminate y, you eliminate the vertical component, so you're just looking along a particular vertical line at x is equal to something. And that makes sense because we need to make sure that that on that line that the 2 lines we have meet up, and similarly for y. So geometrically it does work out. It's a little weird to think about, but it will work. Okay, now we want to just make sure to get some more practice. Okay, so as you're comfortable, pause the video, try these out, resume the video when you want to hear more. Alright, for this first one, it's not exactly clear what you should multiply each equation by, or the equations by, because, I mean, you can't multiply 2 and get 9, you can't multiply 3 and get 2. Well, you can, but not by a nice integer. So what I'm going to do is I'm going to multiply this first equation by 2 to both numerator, or to both sides, and then the second equation I'm going to multiply by 9. Okay, and I'm going to hope to eliminate the y's. So if I do that, I'm going to get the system that is 4x minus 18y is equal to 2, and then 27x plus 18y is equal to 153. Okay, and then if I add those, okay, I'm going to get 31x is, and then the 18s are going to cancel, and I'm going to get 155 here. And if I solve for x, I just get 5. Huh, what luck. That was nice. Now, to find the value of y, I can pick either equation and substitute that in. I'll pick the first one. So I'm going to get 2 times 5 minus 9y is equal to 1. This is 10. Move that over. I get minus 9y is equal to minus 9. Y is equal to 1. And I should check this using the other equation. So 3 times 5 plus 2 times 1 is equal to 17. 15 plus 2 is 17, last I checked, so that works. And I'm going to say the solution set the solution set is bracket parentheses 5 comma 1. Alright, and I will have solved the system. Alright, for the second one, I want you to try it out and see what you get. You try it out and you don't get far and you get 0 is equal to 0. Well, okay, what do you do in this case? It's a true statement, right? 0 is equal to 0 anytime. So when this happens, this is actually called a dependent system, okay? When you get a true statement regardless of the value of x and y, this is an example where you get a dependent system, okay? In this case, what you're going to say is that you do have a solution set. Also, this is the same as saying there's infinitely many solutions, okay? The solution set is going to have a particular form. Set is, and then bracket, and you need to still specify a value of x and y, but here's what you're going to do, okay? You're going to pick a variable. Maybe in this first equation, you want to isolate x, okay? So x is equal to 5 minus 3y, okay? Now, when you say that, that's saying that to compute x, you have to have a function in y. So you're saying x here is instead 5 minus 3y, and then you have a value of y, and then you're done. So now, theoretically, all you would have to do is specify, let me do this in different color, specify a value of y, and once you do, you get the corresponding value of x, and that actually works for any value of y. Okay, so when we have a dependent system, the solution set looks a little different, but you can still write it down. Okay, the only place where you're not going to really be able to write the solution set is when you have an inconsistent system, when you have no solution. But even still, we have the empty set there. All right, so elimination is perhaps a faster method to substitution, maybe, maybe not. It's kind of up to your own personal preference, but if there is a desired solution method, it will be indicated in the instructions. So determine the solution set by using the addition method. Okay, the other one said substitution methods. If it's not stated, you get to choose. Have fun.